Hello everyone. So this is the week 4 of the NPTEL course on Introduction to Algorithms and Analysis. And in this week, the primary topics that were discussed were linear time sorting, uh, and in that there was counting sort, uh, and also discussion on like stable counting sort, like what does it mean for a sorting algorithm to be stable. Then there was Redux sort that uses counting sort in a smarter way, followed by bucket sort. And then there was a discussion on statistics of the running order of the algorithms, right? And then followed by randomized order statistics, and followed by worst case linear time order statistics, right? So what we'll do is we'll go over some of the parts of counting sort, like all the sorting algorithms, and some other example questions that you might have in your weekly assignment. So let us start with counting sort. So the main feature of counting sort is that there is no comparison between elements, right? So this is not a divide and conquer kind of algorithm, right? Or we don't compare any any of the two elements here, like as we were doing in the, let's say, heap sort, right? Where we were finding the maximum and then comparing the node to its child, right? To max heapify the tree. For example, we are comparing if the value of this node is like greater than or less than the value of its child nodes, and if it was less than the child node, and if we had to max heapify, then we were just comparing and swapping these two, right? So this kind of comparisons are not there in counting sort. So I'll write the pseudocode also once. So given an array A, right? And this array A is indexed with indices I, right? This is AI. So what we do is we make two more auxiliary variables in this, right? So I goes from 1 to n, So we define B also of the same size, that will be basically the sorted array, right? And then we also define another uh, auxiliary storage called C, and the index of C goes from 1 to the maximum value, right? Or the maximum, the value of maximum element in A. And the pseudocode for it goes like this. So start with I going from 1 to k. So this is to primarily just initialize the auxiliary storage with 0, right? And then what we do is we basically count the number of values, right? So what we're going to do is, so we're going to index into the value of the element of A, and we are going to increment it by 1, right? So we are essentially counting each value of A, right? Each individual independent element of A, right? Unique element of A. And then followed by uh, we update all the values in C, right? That are the count of the of the individual elements or the unique elements of A by the uh, basically we are just trying to form a hierarchy like this inside the array, right? So it's like a cumulative distribution. It is very analogous to cumulative distribution, if you want to call that, right? So if let's say the A had values, or let's say C has like contains from 1 to 3, 4, 5, and it has one, let's say 2 times, 3 1 times, 4 also 1 time, and 5 3 times, right? Let's just say. So what this does to C is basically it forms, and so this will be 0. So this forms a cumulative distribution like this, right? So now the resulting values in C will only be in increasing order. So this will be 2, 2, 8, and then 2 and 1, 3. This will be 4, and then this will be 7. And after we form this, then what we basically have to do is we just have to choose the index. So the next step goes like this. From n to 1, and then we update B, the array B, based on the count, right? So this count, since now it is only increasing, it essentially forms the index, because now if we index it, let's say the first value, right? So whichever values these are, you just so this is now basically a sorted version of the array, right? Um, if we just start counting from 0, right? So whatever is the count, cumulative count of A of j, that is used as the index. Again, we discussed why it can be used as the index of A of j, right? And then the since that element is sorted, we basically remove its effect from the counter, right? Um, that particular element has been accounted for. So this is essentially the pseudocode for counting sort, right? And let's take an example. Let's say the array A that we are working with is 5, 4, 1, 2, 6. Let's just say, right? So our A is this, and then C will now be of size 6, right? Right, so 1, 2, 3, 4, 5, 6. And let us repeat some values also, right? Let us repeat 2. So we do the first loop. So the first loop is basically initializing Ci with 0. Second loop is going through A and using the value of the element of A as the index of C and incrementing it by 1, right? So after second loop, right? So we are trying to do this, right? So at position 5, the value will be 1. At position 2, 2, 1, 0, 0, 1, right? And then followed by the step of accumulating C, right? 1, 3, 3, 3, 4, 5, right? So now this gives us the indices of the respective values of A, like the sorted indices. So the last step was using the counter as the index, we update the values in B, right? And J goes from n to 1, right? So J decreases. So for J equal to n, and n here was 5, so the last value, right? 6. And the index for that value is here, right? 5. So B 2, 3, 4. Yeah, so 6 goes into the fifth index. 3, 4, 5, right? So 6. And then 2, uh, so for the index for 2 is 3, right? So it goes here, and then we decrement the counter for this, so that the next time we encounter the same element or the element with the same value, we put it at a index lower than, like, there is no conflict of the index, right? So then we encounter 1. So 1 uh, is here. So the index for 1 is 1, right? And then we come to 2. So for 2, it was 3 before, but then we subtracted 1, so it had become 2, right? So it goes into the index 2, and it also now reduced by 1. Let's just write C separately here, right? So this became 4, this now is 1, this is now 0, 3, 3, 4. Okay, and now the last element 5. So at position 5 we have 4, right? So index for the element with value 5 is this. So we end up with the sorted array, and we sorted this using only the counts for the individual elements, right? So we counted the number of elements, then we formed the cumulative count of the elements, and then we use that cumulative count as index to basically arrange all the values in increasing order in another array, right? So now if you also see that if I put this as 2, 1 and 2, 2, they come into the same order, right, in the final sorted array, right? So this kind of sorting is termed as stable sort, right? Stable sorting algorithm. And also note that there are no comparisons here, right? We never compared any of the values. The comparison was done automatically by counting by these two steps, by counting and then taking the cumulative count, right? Let's take one more example question that you might have in your weekly assignment. So the statement is that there exists a comparison sort of five numbers that uses at most six comparisons in the worst case, right? So we have to tell if this statement is true or false. So for comparison sort, we know that the runtime is basically n log n, right? But in this case, we are not concerned with the average or the best runtime. What we want is the worst case, right? And the worst case for comparison sort, for example, quick sort, is of the order of n squared. So if we have five elements, like there would be approximately, so the time order will be approximately uh, 25, but the number of comparisons will be more than that, right? So this is basically false, right? And if we have to dig a bit dig a bit deeper in this, then what we can say is that the number of leaves in a decision tree for sorting five numbers is at most 5 factorial. right? And the height is the log of the number of leaves. So the number of comparisons that are required uh, depend on the height of the tree, right? And if we analyze log of 5 factorial, right? So basically 5 factorial is 120, right? And 2 to the power 6 is 64 and 2 to the power 7 is 128 and 5 factorial lies somewhere in between. So since log is a monotonous function, so log of, so we can write 2 to the power 6 is less than 5 factorial is less than 2 to the power 7, right? So we take log of all of them and the signs do not change because it's a monotonous function again. Log base 2 less than log of 5 factorial is less than log of 2 to the power 7, right? So we end up with this inequality, and this shows that at most we need 7 comparisons, right? We need at least 6, but at most, like not at least 6, but at most we need 7 comparisons and not 6. So this statement is false. Let us take one more example. In the worst case, second smallest of n elements can be found with how many comparisons, right? So the options are 1 minus ceil of log n minus 2, n minus ceil log n minus n plus, and then n plus 2, and then d is log n ceil plus 2. Right, so if we want to find the second smallest of n elements, right? So to solve this, we see that first, and we want the worst case scenario, right? To find the minimum element, n minus 1 comparisons are required, right? And when we are finding the minimum element, right? So when we are finding the minimum element, each element is compared at most log n times, right? Because every time we compare the elements, right, uh, in the halves, basically, right? Because first we'll search for n, then n by 2, and then in each iteration, we keep halving the space in which we look, right? And then at the end, there is only one element left, right? So, of course, like for the second comparison, at most log n comparisons are required. So, at the end, to find the second minimum element, we need n plus log n minus 2 uh, comparisons to find second minimum element. Now let's take another one. Let's discuss before this Reddick sort. Right? So uh, in Reddick sort, what we do basically is we divide the numbers, right, into, I mean, this is the array, and we divide the numbers into chunks, right, of bits, equal chunks. And in the subarray of every chunk, we apply counting sort, right? So, of course, we know that counting sort is of the order of n plus k, where k is the highest value of the uh, highest value of the elements of the array, right? And since we are doing it for the number of chunks we have here, uh, the time complexity for Reddick sort is order of d times n, right? So order of n for each counting sort, and then d times for the number of chunks. that are created. The number of digits. So I think one good example is already given in the lecture. Uh, let's take an example on this. If we use radix sort to, let's say, sort n integers, where each number is represented as a 4-digit base n number, right? So again, so here we create bases, and every base contains a certain number of digits, right? And that is what we took here. Like, this is the number of digits for the particular base that we divide it in. So here we are given a four four digit basis, right? Then the time complexity is it is log n squared or n cube. Okay, so the worst case time complexity is not what we are asking, right? So worst case time complexity is basically when d becomes of the same order as n. So like in worst case it becomes n squared. This is not we are asked here, right? So uh, if we consider that n is much larger than 4, right? That is the number of digits that we are given here. Then it becomes O of 4n, right? And like time complexity of radix sort. And since n is very higher than 4, we can write it as just O of n, right? So it's a approximately linear time algorithm. Let's take one more example. Using counting sort, how many comparisons will be made to sort the array 9, 7, 13, 28, 22, right? And the options that we have are 5, 5 to the power 4, 5 to the power 5, or 0. So this is essentially just a conceptual question. It is not a numerical. Because if we remember that in counting sort, there are no comparisons, right? We never make comparisons in counting sort, as we saw above also, right? We never directly compared any of the two elements. We just counted these elements and then we made a cumulative counter, and then we indexed into that. We never compared any two values, right? So if we are asked like how many comparisons are made in any implementation of counting sort, the answer will always be zero, right? Because there are no comparisons that are made. We take one more example that the what is the auxiliary space complexity of counting sort. We are given these options. So here we are being asked about the auxiliary space complexity of the counting sort. Okay. Option C, order of log of log n and the n plus t, where t is the range of inputs. Okay. So again, the auxiliary space depends on, of course, the range of input, because the size of the auxiliary array C that we make depends on the maximum value of A, right? Uh, Maximum value of A. So it depends on the range of input linearly, since you can see like space complexity, and also it has to hold all the individual values of N, and potentially the values can go up to N as well, right? So it depends on both N and T and linearly. So it's order of N plus T. So I guess you'll mostly find these kind of questions in this week's uh, problem assignment, in this week's assignment, and I think I'll stop the meeting now. Thank you.